So we have this graph that shows us the optimal allocation of pollution permits if we allow a tradable pollution permit system. So the graph shows the marginal cost of pollution reduction for two different firms. Um, and notice that we have the axis on the bottom, the horizontal axis, is moving in opposite directions for the two firms. So we've graphed the marginal cost of reduction for firm one moving from left to right, and the marginal cost of reduction for firm two, we're moving from right to left. And we know that the optimal allocation is where the two marginal costs cross, because anything to the left of that shows that firm two would be willing to pay firm one for some of those permits, um, a price higher than what it costs firm one to clean up more pollution. And so firm one is willing to sell their pollution permits to firm two because they can get a higher benefit from selling those pollution permits than it costs them to clean up their pollution. So they're willing to clean up a little bit more, pollute a little bit less, because they can get more money by selling those permits on the market. And then anything to the right of that optimal allocation where the two cross is a point where the marginal cost to firm one of cleaning up their own production is higher than anything they could receive from selling a permit on the market. And so they're going to choose to keep their permits so that they don't have to clean up their own pollution. So that's all fine and good as long as we've got the picture. But oftentimes, in the real world, we don't have these numbers or these graphs perfectly nailed down. But even in our sort of fake world of academia, when you're trying to work through these problems in homework and stuff, what you have are equations. And if you're really good with graphing paper or graphing calculator or something like that, maybe you could draw out this picture and come to find your optimum allocation. But I'm not that good at drawing. I don't like to rely on myself to draw pictures when I may not be drawing them to scale or drawing them with perfect slopes and things like that. So the purpose of this video is to talk about how to solve an algebraic example. How to solve these things when you can't draw the picture. So here's an example. This is an example out of the Harrison Roach book, where two power plants are currently emitting 8,000 tons of pollution each for a total of 16,000 tons. Pollution reduction costs for plant one are given by an equation there. Pollution reduction costs for plant two are given by another equation, where, and this is important, Q1 and Q2 represent the tons of pollution reduction. So not how much they're polluting, but how much they're reducing their pollution. So these equations give us the marginal cost of reducing pollution. So now let's suppose there's a tradable permit system that's instituted, which permits emissions of a total of 6,000 tons of pollution. So we divide those permits equally and give 3,000 permits to each plant. So the question is, or the questions are, who will buy permits from whom and how many? So where is that optimal allocation? And if the price of all permits is the same, how much will each permit cost? So first of all, let's think about what happens without trade. So I've taken the important information out of those paragraphs and stuck them up at the top of these slides here in blue. So the initial emissions and the marginal cost of reduction for each firm, and what the new system does. So what happens if we don't allow trade? If we just say each of you is allowed 3,000 tons of emissions, what happens? So each firm is going to have to reduce their emissions by 5,000 tons, go from 8,000 down to 3,000. So the marginal cost of reduction for each one will be what's shown here. So the marginal cost for firm one is that 0.02 times 5,000. So that just comes from the equation for marginal cost for firm one. And then from the equation for marginal cost for firm two, we have 0.03 times 5,000. Again, 5,000 being the amount of tons each will have to reduce their pollution to get from the initial emissions of 8,000 down to the newly allowed 3,000. So we know that if we don't allow trade, we're going to end up at a point where marginal cost for firm 1 is lower than marginal cost for firm 2. And so on the numbers at the bottom aren't the same because we're talking about different levels of pollution here than these. But essentially, if these numbers were correct across the bottom, we are allocating at a point like this one, where the marginal cost for firm 2 is higher than the marginal cost for firm 1. And you can even go further and calculate the total reduction cost, which is the area up under the curve. So the area of the triangle A versus the area of triangles that's D, B, and C. Clearly, the cost of pollution reduction for firm 1 is much lower than the cost of pollution reduction for firm 2. And so now let's allow trade. Because the marginal cost for firm 1 is less than the marginal cost for firm 2, with the initial allocation of permits, with each of them having 3,000 tons, it's beneficial to both firms if plant 1 sells some permits to plant 2, because plant 1 can afford to sell some of their allowed pollution and clean up their act a little bit, because it costs them less to clean up their own act than it costs firm 2 to clean up their act. And so plant 1 will clean up their act a little bit and sell some of their pollution to plant 2, and they can sell it for a higher price than what it costs them to lose that pollution and to have to clean up their act. So the selling will stop when marginal cost for each is equal, as we saw from the graph here. It's always still beneficial for firm 1 to sell permits to firm 2 as long as the marginal cost for firm 2 is higher than the marginal cost for firm 1, and that selling will stop when the two are equal, or algebraically when our MCR1 equals MCR2. So 0.02 Q1 equals 0.03 Q2. So we're looking for those values of Q1 and Q2 when the marginal costs are equal. If we want to be able to answer this question, who's going to sell to whom? We already know who will sell to whom by whose marginal cost was higher in the beginning. But then we want to know how much will they sell. So we want to look at for what are those values of Q1 and Q2. We can solve that if we have one more equation, right? Algebra says if you've got two unknowns, Q1 and Q2, you need two equations to solve that. And so luckily, though, we do have another equation. So we know that the marginal costs have to equal each other. We also know that the total amount of emissions reduction will be 10,000. We know that our total emissions are going from 16,000, 8,000 each, to 6,000, 3,000 each. So the total reduction of emissions in the market is going to be 10,000. And so Q1 plus Q2, reductions for plant 1 plus reductions for plant 2 will have to equal that total emissions reduction of 10,000. So now we have two equations with two unknowns. We can solve those using the algebra that we know. Just plugging in. So what I've done here is I've solved the second equation for Q2. I know that Q2 has to equal 10,000 minus Q1, and I've plugged that into the first equation. So now I have that 0.02 Q1 equals 0.03 times 10,000 minus Q1. And I can just do a little algebra, solve that thing for Q1, and I would get that Q1 equals 6,000. And therefore Q2 must equal 4,000 because our total emissions reduction is 10,000, right? So Q1 plus Q2 equals 10,000. So remember that these numbers, 6,000 and 4,000, are emissions reduction. They're not the total final number of emitted tons. So these are emissions reduction, but we can figure out the final number of emitted tons by knowing where we started. So each firm started at 8,000 tons each. So this means that firm 1 will reduce emissions by 6,000 Q1 and will now emit 2,000 tons. Firm 2 will reduce emissions by 4,000, and so they'll now emit 4,000 tons. This means that Firm 2 has purchased 1,000 tons of permits from Firm 1. If we gave each of them 3,000 and now they end up where Firm 1 has 2,000 and Firm 2 has 4,000, that clearly means that 1,000 of those have been transferred from Firm 1 to Firm 2. So the last question then was, what did firm two pay for those permits? What was the price of the permits? The price of the permits will always equal the marginal cost of reduction in the end. And so we can set P equal to 0.02 times 6,000. So that's just the marginal cost of reduction for firm one is 0.02 times how much they reduced, which was 6,000. So the answer is 120 bucks. Note that's the same thing, exactly the same as if we had plugged this into the marginal cost equation for firm two and done 0.03 times 4,000, which is Q2, we would get exactly the same price of 120. So there's an example of how to work through these problems algebraically when the drawing is not necessarily always as simple as sometimes the book wants you to believe. They just say, oh, draw the graph. You can draw a graph that represents what's going on, but not necessarily is always to scale and easy to solve and things. But now you have the tools to solve these things algebraically if you're just given the equations that you need.